Hey everyone, this is our final project for CS452, and our topic is deep learning on point clouds for 3D shape generation. So the sort of background for this is basically trying to use machine learning and computational engineering. So the idea is being able to generate lots of designs with little human effort in a sort of iterative, nice process, and be able to do, like, for example, simulations on these designs in parallel with generating new ones. So we picked the task to do deep learning-driven 3D design generation, and the idea is basically we want to train on point clouds of 3D objects, along with the sort of ground truth correct value of a signed distance function value, which basically is for a 3D object, how close each point is to the surface of that thing. And the goal is to predict SDF values of a query point. And the goal of this is to learn a compact latent representation of a 3D object and be able to generate SDFs. And this is basically the first step to generating many similar yet novel designs by taking a known latent representation of a known object and then moving it ever so slightly in latent space. And the sort of process for our task, an example of that is shown on the right here, where we have a point cloud of a car, and then we give these points to the model and generate an SDF, which is pictured in the middle section there. And then we can use one of many techniques, for example, marching cubes, to use this SDF and make it into a 3D mesh and then be able to have physical models with it.
So the architecture we went for this is, so there's some key features about point clouds that are going to make this model have to take some things into account. So the first is that it's unordered. Unlike pixels in an image, for example, it doesn't actually matter the order that the points are in your point cloud. But at the same time, they are still geometrically meaningful. If 2 points are close to each other or a subset of points are all close together, that does carry some meaning. So the model should account for that. And then also they're obviously invariant under some transformations, like rotations, for example. And so one architecture that we found in the literature is the PointNet++. So they were using this on point clouds to categorize surfaces, given a bunch of points on the surface, and then the features on those points would be things like color or normal vectors. In our case, the feature is the distance to the surface, the signed distance value, and then the points are anywhere in the space. But anyway, it's very similar to a convolutional layer in a CNN, and that this is a 2D example. Given a set of points, it basically collects them into groups by points that are close to each other. So these groups are all near each other physically in the metric space, and then it just puts them through a linear layer or an MLP to generate, a smaller set of points, and then it just repeats that process. You can see our encoder, obviously the half of our VAE, an important half, is 3 of these layers where the only one feature is the signed distance to the surface. So given the input point cloud, it just goes through these layers, and then a final linear layer into a distribution in the latent space, so a mean and a variance for a Gaussian distribution in the latent space.
So for the decoder, very simple. We have a fully connected layer. We sample, of course, from the latent distribution, and we concatenate our query points. We can pass in many query points at the same time, and then we pass this through a very simple, also decreasing size MLP layer, and in the middle we once again concatenate the query point, as this helps improve performance. As for our methods, we generated our data samples ourselves. We took 1,000 car meshes from the ShapeNet dataset, a very known 3D geometry dataset. We sampled points on the surface, uniformly near the surface, and we had a 9-1 train test split. Our loss function consisted of just a general MSE loss, a KL divergence loss to regularize our latent space, and also an eikonal loss, which is a specific kind of loss that helps regularize signed distance fields, as this is like a physical property. They need to satisfy the eikonal property. And we trained for 140 epochs.
So a major goal of our project was obviously to be able to use this latent space representation to generate new cars, in our case, or new shapes. And so to test that with our model, we randomly sampled the latent code from a unit normal Gaussian distribution, and then we queried the model for a bunch of different SDF values using this latent code. And so over here on the right, you can see we have 2 examples of cars we generated. You can see it just kind of have low values in the middle, high values on the outside, and the slice just at x equals 0 is vaguely car-shaped. And then over on the left, you can see a ground truth, although it's important to note, in this 3D SDF value, half of the points are sampled right on the surface. So this is one of our training examples. And for that reason, you can see the car a lot more clearly than in here, just because the points are actually physically on the surface. But you can see from the slices that we do manage to generate a pretty much vaguely car-like convex structure, which is a success. And then the second way that we measure the success of our model, more qualitatively, is with these visualizations of the latent space. So obviously, for a VAE, you want a latent space that's relatively smooth. You don't want empty sections that don't correspond to any observed data. And we also, you want it to be similar to a unit normal so that you can sample from it effectively and generate realistic new shapes. So to visualize that, we use both TSNE and PCA to kind of project it down into 2 dimensions. And colored it by density here, you can see that they do roughly look like a normal distribution, like a normal ball, a Gaussian ball. But at the same time, there's no clustering or trends. So it's possible that the model is actually not learning it's not being very expressive, it's maybe generating a very similar or random car each time, and perhaps not conditioning on the latent codes as effectively as we would like.
But overall, from our results, we do have a good proof of concept. We were able to implement a model that does do 3D shape generation using point clouds and true SDF values for training, and be able to predict SDF values for query points. And we can even use these use these as predicted SDF values to generate meshes that produce the car-like shape. But however, we did have sort of major challenges along the way, the first of which is data limitations. We only, the sampling that we did was only from 30,000 points, which the distribution of which on and near the surface or uniform in space we described before, but this may be insufficient to fully represent car SDFs. So more data would be great. However, there's also the need to balance the points because while a lot of the information comes from points that are on or near the surface, because that's where the shell of the object is, there's a problem where things like L2 loss would not say the model will end up, because these values, these SDF values, they're so close to the surface, they would be really small. The way the L2 loss would work, we would end up likely having a constant SDF output that's just one small value, and this would end up with low loss, but actually not be very expressive. And overall, the model is not as expressive as we would like because of something like global pooling, which may hurt sort of local features. And some future directions or improvements that we would like to make is we would like to generate new shapes by moving sort of a known representation in latent space, and also to improve our model, we would like to explore alternative architectures, some of which we've tried but we're not able to get good results with, such as graph neural operators, and also we would like to use better positional encodings as well. But yeah, thank you all so much. And extra thank you from me. This will be my last ever Yale assignment. Woohoo!